Hello everyone, I'm Professor Harrison, and welcome back to our module on probability for finance. Today we're going to be covering the log normal distribution, what it is and why stock prices follow it rather than the normal distribution, and how log returns connect the two. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to his family fortune. Today he's trying to put a probability model on the total appraised value of his father Victor's estate. He opens up another one of those mysterious letters. We've been working with the normal distribution, which is symmetric and ranges from negative infinity to positive infinity. That's fine for modeling returns over a short period, but it creates a problem when we try to model price levels directly. Think about house prices. A house in a mid-sized city might sell for an average of $350,000 with prices skewed towards bigger, pricier homes on the right side of the distribution. But a house can't sell for negative $80,000. The price may fall to zero, the owner walks away, the bank forecloses, the property is worthless, but it can never go below that. The distribution has room on the right that it simply doesn't have on the left. That asymmetry is built into the nature of the thing being measured. Stock prices have exactly the same property. A stock at $10 cannot fall to negative $5. The company can go bankrupt, the price goes to zero, but it can never go below that. The normal distribution assigns positive probability to every value on the real line, including every negative value. So if you model prices as normally distributed, you're implicitly saying that there's some chance that the stock price is worth negative, for example, $40, which doesn't make sense. The log normal distribution ends up solving this. A random variable x follows a log normal distribution if the natural logarithm of x is normally distributed. So if the log of x is normal with mean, mu, and variance sigma squared, then x itself is log normal with those same parameters. Two immediate consequences follow. First, x here must always be positive because the exponential function is also always positive. No matter what the value of log of x takes, x itself ends up above zero, so that solves the negative price problem. Second, the distribution here will be right skewed. The right tail is going to be longer than the left. This matches how prices actually behave. They can fall by at most 100%, but they can rise by many hundreds of percentages over long periods. The distribution has room on the upside that it does not have on the downside. So here's the nice thing about working with the log normal distribution with stock returns. The key connection is that if prices are log normal, then the returns are also log normal. So that means the log of the returns are going to end up being normally distributed. Think about why this happens. If the log of price is normal, and P0 is a fixed known constant, then the log of the ratio just equals the log of P minus the log of P0. The log of a constant doesn't add any randomness, so the log return inherits the normality of the log price. The flip side is also true, and it's actually a more intuitive direction. If log returns are normal, then over multiple periods those returns compound multiplicatively. The total price change is the product of all of the 1 plus returns, and the log of a product is the sum of the logs. Now this may seem confusing, but the key thing that we can draw from this is that the sum of many independent normal variables also ends up being normal. So the total log return here is normal, which means that the final price also is log normal. That's the mechanism. Normally distributed log returns in each period produce log normally distributed prices at the end. This makes working with the log normal distribution with stock returns and prices a whole lot easier. On top of this, there's actually an intuitive reason why prices should be multiplicative rather than additive. If a stock is at $100 and moves $2, that's a 2% move. But if a stock is at $10 and moves $2, that's a 20% move. The same dollar amount means something completely different depending on where the price is. Markets don't work in dollar increments, they work in percentage increments. So if we're comparing our two stocks, one that costs $10 and one that costs $100, the normal distribution would say that both have the same probability of having $2 added to them. That's not realistic. In fact, a $2 return on one is very different from a $2 return on the other, which is exactly why we use the log normal distribution instead, which says that a 10% return on one is similar to a 10% return on the other, which is much more realistic. Danny puts down the letter. The letter is addressed to his father Victor by name, and it uses data from Victor's current equity portfolio. This was not just some generic textbook example that the rational quant pulled out. Instead, it was as if the rational quant knew exactly what Victor's actual positions were when they wrote this letter. Danny sets that observation aside and goes back to his math. He's been trying to estimate the total appraised value of the estate. The estate includes a range of assets, property, collectibles, financial instruments, each one sitting somewhere on a distribution of possible values. None of those values can be negative, and the range of possible outcomes is wider on a high side than on the low side. He recognizes the shape. Asset values share the same non negativity property as stock prices. So he applies the log normal model. He estimates a mean and variance for the log of the total estate value using the appraisals that have come in so far, and he builds out the implied distribution. The expected value and median end up meaningfully different. The median is what he'd most likely land near, and the expected value is much higher because it's a log normal distribution. Taking note of this difference, he realizes for the first time that the expected outcome is not necessarily the most likely one. So that's the log normal distribution. When log returns are normally distributed, prices end up being log normal, always positive, right skewed, and with an expected value in median that come apart because of the skew. The key insight is that price processes are fundamentally multiplicative, meaning that they change based on returns, not based on dollar values. The log normal is the natural model for that structure. This log normal distribution ends up being the basis for many of the pricing formulas used in finance, from modeling stock prices to even modeling things like the Black-Scholes equation when working with options.